for the necessary ingredient for a mid-latitude cyclone, upper air support we're talking now. In this picture, it is an idealized 3D view of the formation of a mid-latitude cyclone during the baroclinic instability. In this picture, A is showing a long wave trough at 500 millibar that is lying parallel to the directly above the surface stationary front. In the picture B, a short wave that disturbed the flow upper atmosphere and initiating temperature advection that is representing by blue arrow. Cold advection is representing by blue arrow, and red arrow is representing warm advection. So the upper trough intensified and provide the necessary vertical motion, as shown in the vertical arrows. That vertical motion for the development of the surface wave cyclone. And in C, as the surface storm moves north eastward, it occluded and without upper level diversion air to fill up or fill up, compensate or something, surface conversion air, the cyclonic storm that dying out. So to better understand how a wave cyclone may be developed and intensify into a huge mid-latitude cyclonic storm, we need to understand the atmospheric condition at the surface and at upper level atmosphere, something like 500 millibar level of atmosphere. For instance, suppose that the portion of long wave trough at 500 millibar level that is lying directly above the surface stationary front, as exactly showing in the picture A. On the 500 millibar chart, contour lines that are representing the gray line over here, uh, and isotherm that is the dash gray line in picture A, that those are parallel to each other and those are crowded close together. So colder air is located in the northern half of the map, while warmer air is located to the south. So winds are blowing at fairly high velocity. So wind produces a sharp change in wind speed, a strong wind speed shear. So that's it is happening from the surface up to the 500 millibar level. So suppose that a short wave moves through this region and disturbing the flow, um, as you are looking at picture B. This sets up a kind of instability in the flow as warmer air rises and colder air sinks. We know that is called baroclinic instability. So to make the mid-latitude cyclone, um, what is the role of upper air support? So with the onset of baroclinic instability, horizontal and vertical air motion begin to increase the formation of cyclonic storm. For example, as the flow in the upper level became somehow disturbed, it began to lend support for the intensification of surface pressure system. As a region of converging air form above the position you are looking at, position A in the picture B, and the region of diverging air form above the position is showing position 2. The converging air aloft cause the surface air pressure to rise, which is representing as region mark H in the figure B, and surface wind begin to blow out away from the region of high pressure, and the air aloft gradually sinks to replace it. So in the meantime, diverging air in the upper atmosphere causes the surface air pressure to decrease underneath the position 2 in the region that is marked as L, low pressure, on the surface map. This initiates rising air as the surface wind blow in towards the region of the lower pressure. So as the converging surface air develops cyclonic spin, cold air flows southward and warm air to the northward. We can see that is exactly happening in picture B, that the western half of the stationary front is becoming cold front, and the eastern half of the stationary front is now warm front. So cold air moves in behind the cold front, and while the warm air slide up along the warm front. So this region of cold and warm advection occur all the way up to 500 millibar level of atmosphere. So in the picture B on the 500 millibar chart, a cold advection is occurring as position A, which is indicating blue arrow, sorry, as wind crosses the isotherm and bringing cold air into the trough. So cold advection makes the air more dense and lower the height of the air column from the surface of up to 500 millibar. So consequently, that the pressure in the trough is lower and trough is getting deepened. The deepening of this upper trough caused the contour line to be crowded close together, and the wind aloft is to increase. Meanwhile, at position 2, if you are looking at the red arrow, warm advection is taking place, which has the effect of rising the height of a column of air. So here, the 500 millibar height increase and a ridge built. So this ridge is high pressure, is strengthened. So the overall effect of that differential temperature advection is to amplify the upper level wave. As the trough aloft deepen, its curvature increase, which is turn increase the region of diversion uh, above the developing surface system. At this point, we can say the surface mid-latitude cyclone rapidly developed as the surface pressure fall.